So if we have to describe our particles as a wave, then we can assume that there's going to be some function, let's call it a wave function, that describes the particle. So our wave functions are typically given the symbol psi, Greek letter psi. They're a function of the position, x, y, and z, and time. And these wave functions are well-behaved, meaning that they are single-valued, and they are continuous, and they are finite. They don't go to infinity anywhere, and they are square integrable. The reason that our wave functions have to have these properties has to do with how we are going to interpret this wave function. So this wave function is a periodic function, typically, just like a light wave is a periodic function. So we typically think of light waves as being sines and cosines. So we'll draw a sine wave here. So it's a periodic function, right? And it has some amplitude, and it has a wavelength associated with it, and it has a frequency, how fast it goes from one peak to the next peak. The amplitude of this wave is associated with its intensity, and it is the amplitude squared that gives us the intensity of this wave. The intensity of the wave is like, for the particle, is like how much of the particle is at a given place. So the amplitude at any given x value is its intensity at any given point in space. And so for the particle, we're going to do the same thing. We're going to take the square of the wave function, and we're going to associate that with the probability of finding the particle, or the intensity of the particle, at any given point in space. So a couple of things about these wave functions makes this a little bit tricky. So in general, our wave functions are complex functions. In other words, they involve the imaginary number I. And also, they have units, typically, of per meter cubed for a three-dimensional wave function, per meter squared for a two-dimensional wave function, and per meter for a one-dimensional wave function. So if we are going to associate the square of that wave function with a probability, we know that probabilities are unitless. So really what this tells us is what's called the probability density of the of the particle, meaning the probability per volume for 3 dimensions, per square meter for 2 dimensions, and per meter for 1 dimension. So if we want this to be a true probability, then that means we have to take the wave function squared times a volume element, and then that will give us a probability, a true probability in terms of unitless number. Now, the other issue we have is, how do you square a complex number? So to square a complex number, you have to take the complex conjugate times the number itself. So when we write psi squared, we mean the complex conjugate times the wave function. So the first important concept is that this probability density times the volume element is going to be the probability of finding the particle between the points x, y, z, and x plus dx, y plus dy, z plus dz at the time t. So the probability of finding the particle at some point, x, y, z, within some particular volume element around x, y, z. So the consequences of this are that psi square psi, so psi squared, has to be equal to 1 when I integrate over all of space. So if I integrate over dx, dy, dz over all values of x, y, and z, all of my probabilities have to add up to 1. So to be a good probability, if I add all probabilities, they have to equal 1. Now d tau is our shorthand for the volume element dx, dy, dz. So that means that I have to be able to integrate the square of this function over all space, and it has to give me a finite number. It has to be equal to 1 over all space. So that we say that this is square integrable. In other words, I can integrate the square of the function, square integrable. And that has to be true if I am going to interpret this as a probability. So that's the first thing. The second thing is that psi has to be finite. And if it's not finite, if it goes to infinity at any point, if it goes to infinity at any point in the domain of x, y, and z, then this integral is going to go to infinity, because if you add up something that's infinite to anything else, you get an infinite number. And so it won't be square integrable if it's not finite. So psi has to be finite. Psi has to be continuous, because if I'm going to interpret this as the probability of finding the particle, then I can't have a place where there's no defined probability. So if my function is not continuous, there will be a jump in the function. There will be a point where that particle doesn't have a defined probability. And so it has to be continuous if I want to have a defined probability throughout all the x, y's, and z's that my particle can take on. And then it also has to be single valued, because I can't have my particle have two different probabilities at a given point in space. So let's see, if I have a function that is continuous, then there's no jumps. If my function is discontinuous, then I might have something that looks like this. And so in this region right here, I don't have a defined value of the function, and so there's no defined probability. That's discontinuous. Can't have that. And then if it's not single valued, so if I have a function that's not single valued, it might double back on itself like this, and then at this x, there are 1, 2, 3 different values of the function, meaning that the square of the function has 3 different values, meaning that there's 3 different probabilities for the particle to be at this x. So I can't have this. So it can't be non-single valued. So that's why our functions have to be finite, continuous, single valued, and square integrable.